So I wanted to just set the scene a little bit on our session with novel approaches to detecting life and intelligence beyond Earth. So I'm the project scientist for Breakthrough Listen on the Green Bank Telescope, and I'm also the director of our undergraduate research program. It's great to see many of our undergraduate interns here today. Amazing experience for them to be at this conference. We also take them on field trips up to the Hat Creek Radio Observatory. We get them hands-on with some cutting-edge radio equipment, the GNU radio equipment that you can see here in this picture. I hope you get the chance to chat with some of the interns that are here during the rest of the meeting. They're all great folks. So I wanted to begin with an artist's impression of all of the planets that were known outside of the solar system when I was in high school. The situation has changed in the last sort of 30 or so years. We still don't have great pictures of any of these planets. Of course, the Breakthrough Starshot initiative aims to send a small probe to the Alpha Centauri system, and hopefully we'll get some great pictures back from that. We've heard about ideas of using the sun as a gravitational lens to image some of the planets around nearby stars. But we're really sort of still in a discovery phase of sort of understanding really how common planets are and trying to understand whether any of these planets are inhabited other than our own. The habitable zone in our solar system is the region where liquid water could exist on the surface of planets. And similarly, habitable zones are found around other stars in the galaxy. But these are not necessarily the only places that we could look for life, and we've heard indeed a little bit about looking for life on places like the icy moons of the gas giant planets, maybe sort of life as we don't know it that could be maybe not even bound to a planetary system. And so there's a lot of places to look. We don't really know the answer yet to how common life is, but we know that there are many places where life could arise. There are hundreds of billions of stars in the Milky Way galaxy, and we now know, as I say, sort of the results that have come out just in the last few decades that many of those have planets, and many of those planets themselves are habitable. And of course, our galaxy is also one of hundreds of billions. This is the Hubble Ultra Deep Field. It's about a 1,000,000-second integration, looking at a region of sky that is about the size of a grain of sand held at arm's length. The star near the center of the picture here, one of the brightest stars in the field, is about 100,000 times fainter than you could see with your naked eye. And so this is a region of sky that would appear just completely blank were you to look at it with your naked eye. But it's full of galaxies. There's about 10,000 galaxies in this image, and these are repeated all over the sky. So essentially, even in our observable universe, there are maybe something like 10 to the 22 places where life could potentially arise. And so you have to ask yourself, we have the ingredients, we have the conditions, is that sufficient, or is life nevertheless very rare? There are really three methods of how we can do astrobiology, the search for life. One is to sort of go there like the Mars rovers have done and kind of sniff the dirt and see if you can detect those signatures of life, either current or past, directly. One is to do remote sensing for biosignatures. And another is to look for techno-signatures. And so what has traditionally been called SETI, the search for extraterrestrial intelligence, but by analogy with biosignature searches, the idea here being that if intelligent life develops technology, some signs of that technology could potentially be detected even at fairly large interstellar distances with nothing more than the current technology that we have. Both of these fields really began sort of in the late 1950s and early 1960s. So NASA formed an exobiology research program in 1960. Frank Drake did the first SETI experiments at the Green Bank Observatory in 1960. Frank had a single channel receiver. He observed 2 stars and sort of tuned through the radio band. We now have, with Breakthrough Listen, a receiver that's capable of digitizing many billions of channels at a time at Green Bank, and we're looking at thousands of stars. And then we're moving on, and you'll hear a little bit about our programs on array-based telescopes later in this session. We're moving on to look at millions of stars. So really sort of a sea change in terms of our ability to survey these potentially habitable worlds. Talking of Frank Drake, this is the Drake equation, which probably many of you are familiar with. And again, We really didn't know what many of these numbers were until fairly recently. So n is an attempt to parameterize the number of communicating civilizations in the galaxy. And we get this by multiplying the rate of star formation, which is probably something like 5, depending on sort of how you measure what kind of stars you're looking at and this kind of thing. We multiply that by the fraction of stars that have planets, and again, we now know that is probably close to 100%. And the number of Earth-like planets per star, which is probably something like 1/5. And now we get into the numbers that we don't know. So we have the fraction of planets with life, and this is what the astrobiology experiments are attempting to measure directly, to actually go out and sense life on these planets, but we don't know what this number is. The fraction of planets with life that develop intelligence. We only have one example here on Earth, so this could be anywhere between 0 and 1. The fraction of that intelligence that develops the ability to communicate. And you can define communication however you like. Here it could be radio communication, it could be optical communication, there could be sort of means of communication that we don't recognize as communication potentially, so maybe you don't want to include that in this fraction. But essentially what SETI experiments, what technosignature experiments are trying to do is to measure n directly, which will then get us the products of these numbers. And then you have L here at the end, which is the lifetime that that civilization is communicating, the lifetime that the communicating technology exists. We've heard a lot in the news recently about sort of some of the existential threats to humanity, about sort of artificial intelligence that might take off and destroy the planet or decide that humans are superfluous. And so to some extent we're looking to measure this Drake L and the product of all of these numbers. And in fact, if you are optimistic and you think that life is inevitable, you think that intelligence is inevitable where life happens, and if you think that communication is inevitable, then what you end up with when you multiply these numbers together is n equals L. So the lifetime of the transmitting civilization really determines the number of civilizations that are going to be out there. And so this has been termed the archaeology of the future. You find out what happens to civilizations on average by measuring n or by putting constraints on n. And indeed, Breakthrough Listen has put some of the most significant constraints on Drake's n of any project to date, and continues to do so. So again, if you're an optimist, you might think that n equals L. And Frank Drake himself is an optimist. This is his license plate. You can see with the UC Santa Cruz license plate holder here as well. Frank is an emeritus professor here at UCSC. And Frank thinks n equals L. So I think Frank is sort of somebody that we all try to emulate in his great contribution to the field. And I think again the fact that we didn't know how many planets there were around other stars when Frank started these experiments, and that he still has sort of this optimism that we should be going out and trying to make these measurements, I think is inspiring. So the topic of the conference is innovations for a low-cost future. So what innovations can we make in the field of astrobiology? Well, one is we have these big single dishes. Here's the GreenBank telescope, 100 meters in diameter, with our chief engineer, Dave McMahon, for scale. And you'll hear today from a couple of our speakers about how we're moving to array-based telescopes. I mentioned how these are going to enable us to do our million-star survey. So the big single-dish telescopes will still have a role to play. But we also, rather than having dedicated time on some of these array-based telescopes, can subscribe to the data that's flowing out of them and do commensal observing, where we're not driving the telescope per se, but where we're looking at targets that are interesting within the field of view. We're also going to hear about wide field of view telescopes in the optical, particularly high throughput telescopes in the optical. Here, the Vera Rubin Observatory. So this is essentially sort of making movies of the sky, sort of IMAX movies of the sky, really at optical wavelengths, and how we can use that to discover anomalies. A lot of SETI is also about sort of generalized anomaly detection. And then, in the biosignature field, which of these is going to win out? And we'll actually have sort of a poll on this later on. Do you think that we should be betting our money on making a detection of intelligent life, or do you think that simple life is common? It sort of depends on what you think those parameters in the Drake equation are. And so, I think these are both fields in which we should be investing. But you'll hear from Jason about how really these are sort of two horses in a race, and we don't know which one of them is going to win. We're also going to hear a little bit about essentially some of the puzzles of life, about why the molecules that make up living organisms on Earth have a chirality. So that helps us sort of puzzle how life got its start on Earth. And we're going to hear about interesting methods of detecting life using nanopores, and how this might enable us to do some of the missions that you've heard, these low-cost, fast missions going to other worlds in our own solar system, and how we might be able to use some new low-cost technology to make those detections. And I wanted to leave you with a couple of sentences from the 2020 Decadal Review of Astronomy. It's an exciting time in which to practice the astronomical craft, as humanity edges ever closer to being able to answer the age-old question, are we alone? It's humbling and exciting to contemplate that the question of whether life exists elsewhere could be answered with a technology humanity now possesses.